Welcome everyone, I am Pramod Beesal, IT Delhi graduate and currently an RSME officer, IES 2017 batch. In this video, we are going to discuss about the coordinate systems, and coordinate transformation from one frame to another frame, and also the HTM, that is Homogeneous Transformation Matrix or the Homogeneous Coordinate System. And after watching this, you will be able to answer these two questions. One is from prelims 2018 that says which one of the following statements regarding homogeneous transformation matrix are correct. So after watching the full video, you will be able to look at the various properties of a transformation matrix. Then there was a question in 2017 mains which says to determine the missing elements from a frame transformation matrix that was given to us. And then there is one practice question also that we have aligned here, and in this we are given the coordinates of the origin of frame 2, and with respect to frame 2 the coordinates of a point, and we need to determine the coordinates of that same point with respect to frame 1. So all these things you will be able to answer after watching this full video. So in order to understand the concept of coordinate transformation matrix or the homogeneous transformations, we need to understand what is mapping. So in mapping, basically what we are doing is we are assigning multiple number of frames to define same point itself. So we are simply changing the description of a point in space from one frame to another frame, whereas the point remains same. So only the description is changing, the point will remain same, and there can be three possibilities here in order to define the relationship between these frames with respect to each other. So what will those three possibilities will be? One possibility that there can be translation. So one frame will be defined with respect to another frame in terms of translation only. Second, it could have been a rotation only. And third, it can be a mixture of translation as well as rotation. So a translation plus a rotation. We may have all these three possibilities with respect to the frame shifting from one point to another point. So when I say that I am having translation, and I'll be taking 2D examples as well as 3D examples so that it will be easier to understand and to correlate things, right? So in terms of translation, what I will say, let's say this is my original coordinate system XY. So that will anyways remain same for all of them. So that is my original coordinate system XY. Now when I am having a translated frame, so this is my frame 1. Frame 2 I am representing with the help of translation. So somewhere here I will be having my UV frame. And there will be these distances in order to define the distance between origins, right? So that is translation. If I am having rotation, then origin will remain same, but there will be a angle with respect to the axis. So UV rotated at some angle theta. And if I am having translation plus rotation, means the origin has been shifted, as well as the axis have been rotated with respect to each other. So it could be U, and here would be my V somewhere. Usually when we are talking about two different frames, then one frame we assign with the help of XYZ and another frame we define with the help of UVW. Now this is what we do in 2D. Now if we talk about 3D, in 3D also we can have same possibilities for the frame definitions and everything, right? So let's say this is my XYZ frame initially. So I can have again all these three possibilities here also, right? This is my let's say X, this is Y, this is Z, X, Y, Z, X, Y, and Z. All these coordinates I am all these coordinate axes I am having over here. If I am only doing the translation, then the origin will get shifted to some other location. So it is a new location over here, which is having U, V, and W. So this origin and this origin are having some three perpendicular distances along X, along Y, and along Z. If I am having only rotation, means this is U, this is V, and somewhere here I will be having my W, right? That is only rotation. And if I'm having a combination of these two, then it would have been shifted also, as well as it would have been rotated with some angle, right? And that is my W. These are my axes. This is theta and all these things we are having. Now, how do I correlate any single point? Let's say this is my point over here. Okay. And this point, when I talk with respect to coordinates x and y, I will call it as 1p. Means point P with respect to frame 1. Okay. So 1p will be having x comma y coordinates. When I see the same point with respect to v and u, I will call it as 2p. 2p means point P with respect to frame 2, and it will be having the coordinates u comma v. Now what will be the correlation between 2p and 1p? Okay, just so you understand it better, let's say this is the same point I am having. Okay, now the vector joining from here, from the main origin, this will give me 1p basically, means coordinates of point P with respect to frame 1. And if I look at the same point from this origin, that will give me 2p. Now this 1p and 2p will be having certain relationship with each other that we give with the help of a transformation matrix. Now let's have the derivation for the transformation matrix for rotation as well as for translation in 2D, and then we'll have 3D also. Okay. So when I'm having 2D rotation, okay, see, translation we don't have to do anything, we will simply add the values together. Okay, so x, y, z plus whatever dx, dy, dz we are having, we'll add them together and we'll get our new coordinates with respect to 2p or 1p. We can get them very easily, right? But when we are having rotation, it gets a little trickier. That is why I'm going to derive it, so that you will be able to understand the formula as well as you will be able to remember the formula. Okay, so let's say this is my x, y coordinate. Okay, and there is my point, this point P. Now I am having another coordinates because I am having a rotated frame, right? So I have rotated a frame u, and let's say this is my v. Okay, uv frame is there. Now the same point with respect to frame xy will be having these lengths, right? So this will be x and this height will be y, right? So I will say that this height is y, right? When I am having the coordinates as xy. Okay. Now at the same time, if I have the coordinates as u comma v, then what will happen? Now this length, yani length along the x, this u axis, okay, that will give me the u coordinate. Okay, so this length basically is giving me u coordinate, and this vertical length is my v coordinate, right? I hope you don't have any problem in that. So when I say 1p is basically x comma y, okay, and 2p is basically u comma v. Now what is the relationship between these two? Okay, so I can say that x value is equal to what I will see. This has been rotated with angle theta. So x value can be given by this total length, okay, minus this length, right? So the total length here is u cos theta. So that will be u cos theta minus this length only. Okay, so how much will be this length? In order to calculate this length, I know if this angle is theta, and if I drop a parallel line here, then this angle will be theta, right? And this angle will be 90 minus theta, right? So v cos of 90 minus theta, that will give me this length, and that will become v cos of 90 minus theta, and I can say v sin theta, right? Similarly for y, I can say the y is this much length. Okay, so this plus this. Okay, so this much height is u sin theta plus upper height is v cos theta. Okay, so now I have that x, y and uv relationship. If I want to represent it with the help of a matrix, then I can say that xy is equal to cos theta minus sin theta cos theta into u and v. Okay, that matrix representation I can do. So this relationship xy and this matrix and uv, I can say xy is what? My 1p, the point with respect to frame 1, is equal to, there is a transformation matrix and that transformation matrix is between 1, t, 2. So I am going from 1 to 2 and then 2p. 2p is my uv. So that sort of transformation I can use to get the coordinates. The point will remain same, and if I change the frame definition, then I can get the different coordinates with respect to that. Okay, so in case I am given 1p, I can calculate, if I am given 2p, then I can calculate 1p from here. If I am given 2p, then I will say what? 1t2 inverse into 1p. Okay, now what will be the relationship is 1t2 and 1t2 this inverse? So 1t2 inverse is equal to 1t2 transformation, and that is my 2t basically. Okay, and a detailed analysis for a 3D matrix that we will be doing in our homogeneous transformation matrix analysis. Now that we have done the 2D transformations, now let's have a look at the 3D transformations. If we talk about 3D, then same vector will be representing a point. If I am looking at xyz axis, then I can say that my vector is vx, vy and vz basically. Okay, and when I am looking at same point from u, v, w axis, then I can say that it is vu, vv and vw, right? These sort of vectors I can give definition depending upon which frame we are looking at. Okay, now when I want to see a relationship between vxyz and uvw, then I need to have a sort of transformation matrix between these two, right? So as we did earlier, we are going to do here also. So basically what I am having is v vector is equal to vx into x cap plus vy into y cap plus vz into z cap. That is when we are looking from xyz frame. Okay, at the same time this v vector will remain vu into u cap plus vy v into v cap plus vw into w cap if I look at it from uvw frame, right? Now what I can say is that my vx component will be equal to, no matter which vector I am using here. Okay, so if I take this vector and I need to calculate the x component of it along xyz, then what I will do, simply take x cap dot v. Okay, that should give me my x component of the vector, right? Okay, anyways, you don't get confused here. Just it is just to make you understand how exactly we get the formula over here. Okay, if you don't want it, then you can skip a few minutes over here. Okay, then it will be vu into u cap plus vv into v cap plus vw into w cap. Okay, so basically I am trying to get vx here, and for that what I can do is along x cap I can take a dot product of this particular vector. Okay, that is what I have done to calculate vx. Similarly, in order to calculate vy, I can do same sort of analysis, and vz also I can do same sort of analysis here, and then when I put them in matrix form. Okay, so these three with respect to all of them, when I put them in a matrix form, what I'm going to get is vx, vy, vz is equal to, okay, what will come here? Here I will get x cap, u cap basically, okay, and x cap, v cap, x cap, w cap, and so on. Say, in order to write the transformations, so x, y and z components will be equal to, what is x dot u? That is basically cos theta between these two matrices, two vectors, right? X vector and u vector, because this is a unit vector, so there won't be any magnitude here. Okay, so cos theta between x and u, right? Similarly here, cos theta between x and v, cos theta between x and w, and so on. Okay, and I can get this whole transformation matrix here in order to define with respect to u, v, w. Okay, so again what I am getting here, this is my 1p is equal to, this is what, my 1t2 or whatever the transformation matrix I am having over here, and this is my 2p. Okay, so this is how I get the description or the relationship between two frames which are depicting the same point. Okay, so one we usually call as a fixed frame or the absolute frame, and another we call as a moving frame usually. Okay, so usually the convention is XYZ is my absolute frame or the fixed frame, and UVW is my moving frame. Okay, now if I want to see to apply this formula, this particular matrix for 2D itself, and then I will see what the problem in 2D that I was having for rotation is basically this was my XY, right, and this was my UV. Okay, the one that we have recently derived here only. Okay, this angle is theta. So the first element that I need here is cos theta between x and u. Okay, between x and u it is theta only. Then next element that I will be needing is cos theta between x and v. Okay, between x and v it is 90 plus theta, right? Then cos theta between y and u, this one. Then it will be between y and u is minus 90 minus theta. Anyways, it won't matter whether we are taking the minus or not. Okay, so when I am writing in this matrix, it doesn't matter what direction of angle I take, because cos of minus theta and theta is always same only, and anyways it is a dot product, and in dot product we don't worry about the direction of angle. Okay, so cos theta by u is in this one, and then cos theta between y and v is again theta only. Okay, so the matrix, if I put all these values in this one for 2D, I want to be having the z components, right? So I will be having these components only for 2D. Okay, so I will be putting them here. Then first one is cos of theta, right? Second one is cos of 90 plus theta, and cos of 90 plus theta is minus sin theta. Third one is cos of 90 minus theta, that is sin theta. And fourth one is cos theta, and this was the same matrix that we have earlier got. Okay, so this matrix basically you can remember in order to represent any frame which is binding a point in space. Okay, so that is how we get it here. Fine. Translation, then what we used to do, x will convert into x plus dx, or rather I will say u is equal to x plus dx, right? V is equal to y plus dy, and w coordinate will become z plus dz. Okay, and if I want to represent that in terms of a matrix, then x, y, z, not x, y, z, u, v, w will become 1 0 0 dx, 0 1 0 dy, 0 0 1 dz, and 0 0 0 1 into x, y, and z, right? So that sort of thing I can basically have here, x, y, z, and 1. Okay, now when I want to combine the rotation part as well as the translation part, okay, the third case that we were talking about in mapping, there it will be better to use a common system or a common matrix that is known as homogeneous transformation matrix, okay, or the homogeneous coordinate system. Now what is a homogeneous coordinate system? Let's discuss about that. Okay, so when I talk about a generalized HTM, and that is for 3D, then for 3D we will be having a 4 cross 4 matrix, okay, and for 2D we will be having a 3 cross 3 matrix, right? So this 4 cross 4 matrix is usually known as a generalized HTM, okay, and in that one we have 4 components, okay. So this one matrix will be consisting of 4 different matrices clubbed together, and those matrices will be, okay, so let's say I'm dividing it into 4 parts, right? Now this part here, that 3 cross 3 matrix, is the rotation matrix. Okay, so basically a rotation 1 or 2, from 1 to 2, what is the rotation matrix that we are having over here? Okay, then this here 3 cross 1 is a translation matrix. Okay, or the translation between the origin of 2 frames, I can say. Okay, so this is my 1D2 basically. Then here I am having a 1 cross 3 perspective matrix. Okay, and the role of perspective matrix comes where we have a different points from where we are looking, but in our case, it means in robotics we will be using a 0 0 0 perspective matrix, okay, for robotics. So we don't deal with any other case or any perspective effects, we only describe it as 0 0 0 always. And here we will have a sigma, that is my scaling factor, okay, scaling factor 1 cross 1 matrix, right? And sigma value is always non-zero positive numbers, okay. So non-zero positive numbers we always have as a sigma value. But when we talk about sigma in terms of robotics only, so sigma will be equal to 1 for our consideration. For our use, we will be having sigma is equal to 1 only. Otherwise also, if sigma is less than 1, means more than 0 and less than 1, then we use it for enlargements. Okay, don't get confused here because it's just a notation, and if sigma is more than 1, then we use it for reducing. Okay, so that is like main and basic use of any HTM. We are combining the translation as well as the rotation and perspective as well as scale factors. All these things we are combining together. Okay, so a HTM, basically 1T2 will look like 1R2. Okay, and then there will be a 1D2, 0, 0, 0 and 1. This will be for our purpose. Okay, now that is 1T2. Okay, so if I want to know 1P, then that will be equal to 1T2 into 2P, right? Or if I want to know 2P, then that will be equal to 2T1 into 1P. But what is the relation between this and this? So 2T1 is 1T2 inverse. And as I told you earlier, that for rotation only. Okay, so for rotation only, it can be 1T2 inverse will be equal to 1T2 transpose. But if we are having the translation factor also, what will happen in that particular case? Okay, so what happens when I have a translation matrix also? So in that particular case, we will be having this 2T1 is equal to 2R1, right? 2D1, okay, 0, 0, 0 and 1, nothing here. Okay, so 2R1 is equal to 1R2 inverse, and that is always equal to 1R2 transpose. Okay, that is how we can define the rotational part. But in order to define the translation part, then 2D1 is equal to minus 1R2 transpose into 1D2. Okay, so this is what we have for the inversion matrix, right? So my 2T1 I can say will be equal to finally 1R2 transpose, and here it will be minus 1R2 transpose into 1D2, 0, 0, 0 and 1. Okay, so these are like basic properties of a homogeneous transformation matrix. Okay, so that was the case where we are having the point same location, right, and the coordinate system was changing, right? Now if at all I am having the coordinate system same and my point changes, means the vector definition shall change. In that particular case, I can have my new vector, okay, and that will be equal to my HTM matrix, okay, into my old vector. Okay, so we'll see examples and then we'll have the application of it, the homogeneous transformation matrix. Let's look at the previous year questions. Okay, so the previous question which said we need to check which of the statements regarding homogeneous matrix are correct, and the first statement is considered to be consisting of 4 subsystems. So yes, it is correct, right? We have seen that it is consisting of 4 subsystems, right? Then second statement says upper left 3 by 3 represent position vector. No, they represent a rotation vector. Okay, so this is wrong. Then upper right 3 cross 1 represents a rotation vector. No, upper right 3 cross 1 represents the position vector. So basically they have exchanged these two. So this statement is also wrong over here. And then the last statement is lower left 1:3 represent perspective matrix. Then yes, that is correct. Lower left 1:3 represent the perspective matrix. Okay, so the correct ones are 1 and 4 only. Okay, now we have this one question from mains 2017, and it says determine the missing elements of the following frame representation, which is given here. Okay, if the frame is attached to an object in space, also show the orientation and the position of the frame F with respect to OXYZ. Okay, now this is our frame representation given to us, and these 3 elements we need to determine here. Okay, so how we are going to approach to that and how we are going to solve it. So this is my rotation matrix, or the matrix that connects two frames with respect to each other. Okay, so we have already discussed this one in our 3D transformation. So cos between x and u, cos between x and v, and so on between all of the three axes of each frame, right? Then there will be the transformation part, dx dy dz, and then the perspective part 0 0 0, and the scale part, which is 1. Okay, now based upon the given information here, I can say that my origin of u v w with respect to x y z is going to be at these locations 5 3 and 2. Okay, so dx is equal to 5, dy is equal to 3, and dz is equal to 2, right? These are going to be the coordinates or the position of my frame UVW. Okay, so let's say I am having this frame here, which is at a distance of 5, 3, 2, right? So I have got the position here. Now I need to work on the orientation. So in order to see the orientation, this matrix or the second line here, right, this one. So the second line is giving me the position of v axis with respect to x, y, and z. Okay, and I can see here that since these two elements are 0, okay, so let's make the matrix here to write them all. U, V, and W. Okay, now these two parts are 0, means the angle is 90 degree, right? 90 degrees angle is there. Then it is -1, means 180 degree. Okay, now how do I represent this V vector on this plane? So it is having x 90 degree, y at 90 degree, and z at 180 degree. Okay, so x and y, when both of them are 90 degree, means the line is going to be along z axis. Okay, and the z 180 degree it is having. So if z direction is this, then I will be having my v direction like this. Okay, so this is going to be my v vector. Okay, then at the same time, if I look at the w ones, then it is -1, means 180 degree, then 90 degree, and then 90 degree. These are simple cos value. We can write them 90 degree, 180 degree, 180 degree. Okay, now it is having 90 degrees with y and z, means it is going to be along x. So the angle is 180 degree, means opposite of x. So if this is my x direction, my w direction has to be like this. Right? That will be my w direction. Simple. Now I have calculated v and w. In order to calculate direction of u, what I need to do is the cross product. Okay, I will use the cross product. So what is cross product? X, y gives me z, right? So x, y, z as we have. So x, y cross product gives me z. Okay. Then if I put z ahead, then zx gives me y, and then zy gives me, zx will give me y, x, y, z, z, x, y, and yz will give me x. Okay, so y cross z will be giving me x value here, right? So y is this, z is this, and their cross product y cross z will be upside. Okay, so this is going to be my u axis, right? So there is no problem regarding that. You can verify it using your own cross product with respect to these u, v, and w coordinates. U corresponds to x, v corresponds to y, and w corresponds to z. Okay, so I have now calculated the orientation as well as the position. Now this u is having 0 degrees with y, right, and 90 degrees with x, and 90 degrees with z. Okay, so I have calculated the orientation here. So the missing elements will be, what will be my missing elements, and how will my missing these vector will look like? So these missing three elements, this one and this one and this one, is x and u angle. X u angle is 90 degree, means 0. Then y and u angle, that is 0, and give 1, and then z and u, that is 90 degree, means 0. So that is my three missing elements, and I have calculated the orientation here, and I have calculated the position as was asked in the question. Okay. Now let's have one practice question also here, that frame 2 is rotated with respect to frame 1. So our frame 1 is fixed one and frame 2 is moving one about x-axis by 60 degrees. Okay, so what I'm having here is rx 60 degree. The origin of frame 2 as seen from x is, that is already given as 1d2 757 transpose. Okay, now obtain the transformation matrix 1T2 and also describe the point in frame 1 if 2p is given to me. Okay, so what I need to calculate is 1p and I am given the 2p, so that is equal to basically 1T2 into 2p. And in order to calculate 1T2, what I will be needing is 1R2, the rotation matrix, right? 1D2, the translation matrix, and these elements are 0, 0 and 1, 1. Okay, now 1R2 I can calculate very easily. That is, about x-axis I am having a rotation of 60 degree, and we have already discussed the rotation matrix about x-axis with 60 degree will look like this: 1, 0, 0, 0. Here cos theta minus sin theta means cos 60 minus sin 60, then 0 and sin 60 cos 60. Okay, that is my the rotation matrix with respect to x-axis. Fine, and then D I already have. So finally I can say that 1T2 is equal to, how will this look like? The rotation matrix will come here: 1, 0, 0, 0, cos 60. Cos 60 value is 0.5, and that is minus 0.866, then 0, 0.866, 0.5. Okay, this is my rotational matrix or the rotational part. Then 1D2 is given as 757 already. 757, 0, 0, 0 and 1. Okay, so I have calculated the 1T2 matrix over here. Now in order to calculate 1P, I will say 1P is equal to that same matrix multiplied by 2P, and 2P is 2, 4, 6 transpose, right? So 2, 4, 6, 1 transpose. 1, why have I added 1 here? Because we are using a 4x4 matrix, and whenever we are using a 4x4 matrix in our point system, point coordinate, we always add 1 over here. Okay, so on that 1 I have put here, and when I do the calculations, it will come out to be 9, 1.804, 13.46 and 1. Okay, so these are the coordinates as seen from the frame 1 of that same point. Okay, so now we have seen the previous year questions as well as some practice questions, and that will be all regarding this video. In our next video, we are going to see the composite transformation, that is more than one transformation in one frame itself. Okay, so we will see the concept of pre-multiplication, post-multiplication, and the multiple transformations, and that will be all regarding the transformation part. Well, thank you for watching the video, and best of luck for your exam.